Let me show you how proud I am to be yours. Even stressing us on my floor, still look good.
Hi, my name is Anil Nair, and I'm an aerospace engineering student here at UCLA. And I'm going to help you by going over some math concepts and examples. Good luck.
The example video for extrema, inflection points, asymptotes, and graph. So let's start with extrema. There are two main types. There are maxima and minima. So you can have, there's two types of maximums. There are global or absolute maximums, and then there are local or relative. And the same applies for minima. There are global or absolute, and there are local or relative. So a global maximum means on the entire domain of the function. There's a let's say the maximum is at x equals c. F of c is the global maximum if it's larger than any other point in f of x. Whereas with the local maximum, it may not be the largest point, or it may not have the largest f value, but compared to the points around it, it is larger. And same applies for minimum points. You can have the global minimum, which is smaller than any of the points in the function. Or we can have a local minimum, which is smaller than the points around it. So we have this theorem called the extreme value theorem. And this tells us if f is continuous on closed intervals, if f is continuous on the most continuous intervals a to b, and a is bigger than b, and neither of them are infinity. Then f has a global maximum and minimum on this closed interval. And I'll draw you a little sketch to show you why this must be the case. So let's say this is A, this is B. So we have f of A, f of B. We have to get, since this curve is continuous, we can't make weird jumps like that. We have to get from f of A to f of B. And either our endpoints are going to be the max and min, or we'll go higher than the endpoint, and this will be our max, or we'll go lower than the endpoint, and this will be our min, or both in conjunction. Either way, there is going to be a global max, and more than one point can be the global max. These are all the same y value, so we'll have a global max at all these points. So that's useful because it lets us know that there has to be a global max and min if these conditions are met. to find local maximums or minimums, or local extrema, as they're grouped together. We check candidates. So our candidates are where f prime of x equals 0, or f prime of x doesn't exist. And again, I'll draw you a little picture to show you why. Wherever we have a local extrema on this curve, our slope flattens out of the tangent line. So when the slope flattens out and the function turns around, f prime of x equals 0. So if a function is differentiable, local extrema can only happen when f prime of x is 0. Function is not differentiable, we can also have local extrema at places where the function doesn't exist. So here we have sharp corners, and as you can see, we have local extrema at these brown points. We have a max here, min here, and another max here. Not all places where the derivative doesn't exist have to be an extremum point. For example, this is not an extreme point. It's just a break in the slope. So now if we're looking for global extrema on a domain, then our candidates are again where f prime of x equals 0 and where f prime of x doesn't exist. But we also check the end points of the domain. And once we find these candidates, we need ways of confirming which candidates are maximums and which ones are minimums. So for local extrema, we have two tests. We have a first derivative test, and with the first derivative test, we find f prime of x and locate where f prime of x equals 0. Then we make a sign graph. For example, we have f prime of x, and we know it equals 0 at 0 and 2. And then we check the signs of f, and you see that it's positive, negative, and then positive. If f prime goes from, and also we check where f prime doesn't exist. So f prime goes from positive to negative, such as here, we have a maximal. If f prime goes from negative to positive, I should probably put an arrow or something. F has a minimum, such as here at 2. The slope is going from negative to positive, so it has to change direction. And vice versa. We also have a second derivative test. So if f prime of c equals 0 and f double prime of c is greater than 0, we have a local maximum. And this the f prime of c being greater than 0 tells us we are, or less than 0 means we're concave down. That's why we have a maximum. And f prime of c is equal to 0, and f double prime of c is greater than 0, then we have a local minimum, because we're concave down. So now, and just one more thing. If the sign on the first derivative test doesn't change, let's say we have another thing, 3, and we go from positive to positive, and this also applies for negative to negative, we have neither a max nor a min. And likewise for the second derivative test, if f prime of c equals 0 and f double prime of c also equals 0, we have something that's inconclusive. Examples are y equals x to the third with y double prime equaling 6x. We have a 0. Y prime equals 3x squared, so we have a 0. For y prime, we also have a 0 for y double prime, and the function looks something like that. So we have neither a max nor a min at 0.